Recording of this as well. Welcome back to day 3 of AI Winter, a vastly accelerated introduction to AI technologies. Today we're going to be talking about running and training private AI models. And what this means is if you want to be able to run locally. So this might be literally on your machine, on your laptop. You'll need to have a beefier laptop to do this, but you could with some of the smaller open source models, or on some of the resources on Acre, anything along those lines. Anytime when you need to have a perfectly secure system, or something that you actually yourself want to do additional training on or specialized training on, then today's session is going to be all about that and what the options are for that. So when might you want to do this? You might want to do this if you have a specialized data set that you don't want to share or that is sensitive, or if you simply just want to be inferencing and asking questions, or doing work with, again, data that you want to be held privately. Or you may actually want to do very specialized modifications of these models. So training plus additional modifications of the models. This opens the door. Most of these models are open source. That means you can go in, inspect the models themselves, make whatever changes you would like to do, pull out information that you'd like to have, and then to train your own. So let me go and turn this off, turn this over. Umang, are you kicking us off here, or are we going to be doing this in this order?
I think Abby's going to start.
Yeah. Fantastic. So again, Umang Chaudhry, a data scientist with the DSI. Abby Vigilante is one of our postdocs that you heard from yesterday, and of course, Shara Bell, our senior data scientist and professor of the practice in computer science. I will turn it over to you all.
Okay, hi everyone. Yeah, so I'm unmuted, right? Yes. I'm going to start us off today by talking about specifically inferencing models. So Jesse just referenced that some of these models could also be trained, fine-tuned with relatively low hardware. And Umang's going to tell us a little bit about that. But this is kind of the use case of you don't necessarily want to do any training, but you do want to be able to chat with, interact with your model, yeah, without that concern that you are sending that data over to OpenAI, and even if you check a box that says don't train on it, they probably just do whatever they want with it anyway. So in particular, Llama and then recently Mixtral, which we've referenced, has kind of come out. Those are two models that you probably hear a lot about running locally because they're very popular and very small, and they have lots of different sizes, so people can kind of pick what might run on your own hardware. And so today I'm going to focus on Llama. I believe Umang will also focus on Llama, so you'll hear lots of Llamas today, as kind of these models that run really well on relatively low hardware. So I am on a couple years old MacBook Pro that has an M1 chip from Apple. That's going to be able to run locally a Llama. If you're probably on a number of Windows machines, especially if you had like a dedicated GPU on your laptop, you totally would be able to run this. So don't need a lot of complicated hardware to be able to run these locally for inferencing. And I'm going to talk to you about a couple of options. LM Studio, I think, is relatively recently kind of introduced. And I think that it's kind of by far the best way to do this. There's perhaps kind of similar things to LM Studio, but I think LM Studio is really great. And it's very easy to use, and it has kind of helped reduce some issues that you might have otherwise had while having to run these things before kind of having a nice user interface that they put together. So I'll talk about that first, and we'll kind of do the most in-depth discussion about that piece of software specifically. But there also are a couple of other options that you have for running models locally. In particular, if you wanted a little bit more customization over them, you can get a little bit more easily into the code through these other ways. So we'll talk about them, but not show them as much. Okay. So the first thing to talk about, and yeah, Jesse just posted a link to this in the chat if you want to go and look at it yourself, if you want to start the download, if you just are already sold, because the download's very quick. This is LM Studio, which really is just kind of an all-in-one place way to browse for and download models. It will show you kind of right in the download page whether or not that model is expected to be compatible with your hardware. So it detects whatever GPU you have, if you have one, whatever current hardware you're working on, and it'll show you like, do I think that model will run on your computer, which is really great. Like, honestly, that in and of itself is kind of a nuisance if you're doing this on your own without that kind of thing, just trying to figure out if a model is gonna work on your computer. You can download it right into the piece of software. So it'll download it for you. It'll go find it and download it right there for you. And then you can open a chat using any model you've downloaded and interact with that chat again, right in the piece of software. So that's super convenient. And then they also have a way to start a local server of a model so that I could download a model and sort of open it up within the app, but then go to like Python on my machine and start interacting with the model kind of while that's running separately. So it's really, it has all of these different kind of tools put together in one place for you that makes just interacting with models locally so convenient. So I think I have to stop this screen share and restart one, but I will pull it up and show you what it looks like. Okay, so this is what LM Studio will look like if you download it and open it up. This is your homepage where you're able to just kind of browse. It'll show you like new models or kind of like hot models right now if you've sort of heard of something and you like really want to see what's all the buzz is about. But you can also search for any model. So if I want specifically llama, then I can see what LM Studio has already that matches llama. So you'll notice that a lot, if I search for like Mixtral instead, a lot of the llama or a lot of models are from this Hugging Face repository, which we'll talk about in a second. This is like a really useful Hugging Face repository I have found for like it just like explains models very well. But we can take a look at any of these models, and here it'll show us if the model like is a match. So in this case, it's saying that this type of model is deprecated and I should look for a GGUF model instead. And then here I'm seeing that it should work. I don't know if it'll even suggest it to me, but there is a type of model that I think is AWQ, which is like not supposed to work on Macs at all. And again, I'm on a Mac.
Could I ask,
Yeah.
so these are all models that were that were based on Llama, but had additional training. Is that right? So they've had additional training, both maybe instruction fine-tuning, chat tuning, and they've
Yeah.
all been made available by the bloke on Hugging Face, the website where you can store models in weights and make them available. So is what's happening here is that it sort of simplifies, allows you to go and it will go and get from Hugging Face for you, bring it local, instantiate it, and then run it for you?
Yes. Yes.
Fantastic.
It is finding all of these. I could go and find on Hugging Face with this name myself, but it's going to go and just do that effort for me.
So it's a substantial amount of work that it's saving you.
Yes. And like
Abby,
I
I'm
said,
sorry.
yeah.
I'm sorry if you said this and I missed it. How does it know if it should work or not? Like, what is the thing that it's testing to know that this is a good model for you?
Yeah, so that's a good question. I don't know exactly. I mean,
And by work, do you mean for your hardware and for your GPU?
Yeah, that's what I'm wondering. Like, what is that? I don't mean how. I'm sorry, I asked that question around. I don't mean how is it doing it. I mean, like, what does that mean?
Gotcha.
Does that make sense? Yeah.
Yeah, so certain types of, so I think one function is just like how beefy the hardware that you have is. So if you have a GPU, you're able to run a much larger model. So that's a component of being able to work or not is will the model just like fit within the RAM on your computer, or is that going to fail? But there's also, so I, as a disclaimer, I don't 100% understand this, but these different extensions are different like ways that the model's weights are organized, I guess. And some of those are just simply not compatible with certain computer architectures. So there's a type of this extension that like just flat out does not work on Mac. And so it'll just detect that I'm on a Mac and that's that file extension and say like, that's not going to happen.
And some of those file formats and some of those approaches allow for the model to be split out. So even if your GPU is not as beefy, because you're going to need to have enough video RAM, and some of these it allows swapping out of that. So it runs slower, but it's able to swap out. But others, the entire model image must be on the GPU all at once. And that means that you're going to have on the Windows side, you're going to have a very beefy kind of GPU. But on the Mac side, with the M1, M2 chips, it sort of shares the memory. And so you can actually, even on the M2, like you can get 128 gigabytes, image in there for some of those things. So it's going to detect what hardware you have, whether it can actually run there or not, and if the model is appropriate for your hardware.
Okay. So yeah, then right from this page, if we see that a model could run, we can go ahead and download it. And I'm going to download the smallest of this. I think that okay, so again, maybe Jesse, you could jump in if you, I mean, it might just be specific to this model. There's usually a lot of different like versions of the models that correspond to different like quantizations normally, which is how exactly the weights are stored, the weights of the model are stored. And in general, like you can cut down the size of a model very significantly by doing a different quantization approach, but even if it's of the same model. So you'll notice these are all very different sizes, and I'm just picking the smallest one here, but probably this one also could run on my computer.
Yeah, and the idea here is that all models are numbers stored and then the architecture associated with them. And quite literally, if you're storing a full floating point number, it takes up more space. It takes more bytes to actually to store that. So you could have a model which is approximately the same, but isn't quite as good by simply storing those in smaller sizes, and that's quantization. So you might be moving from a full float to something which is smaller than a float, doesn't have as much information. So when you run the model, it'll still do approximately the same thing, but literally you're losing some of that knowledge because each weight has less. And so, but it's not like it's spreading specific things, just overall its performance is less good. But still, even with heavy quantization, it can still be like 90% of the original, 80% of the original, whereas the size goes to 1/10 or 1/100th. So it can get much smaller. But in some of the most advanced ones, the data types it stores it as are incompatible with certain operating systems. Those quantizations don't exist with some operating systems, but they do exist with others. So you're getting into the real nitty-gritty of optimizing for particular operating systems and hardware. And that's why some models will run in some places and some won't. And so trying to figure this out on your own is a nightmare. So it's a blessing to have something like this, which just tests out your hardware and says, it's going to run, not going to run.
Yes. Okay, so we have downloaded Llama 2, 7 billion parameters chat version. And you can see that there was also a Llama 2, 13 billion parameters. That just means more parameters, so larger model that also had a chat version, but I'm going to go with this one because this is the smallest version of Llama, and I want something to run very quickly and download very quickly. So Oh, I have a server running. Okay, so now that you can see my conversation earlier with this, just making sure that we're gonna work. So now that I have downloaded a model, I can pick one of the models that I've downloaded. So that's okay. So I just downloaded this model, the Llama 2 Chat 7 billion, this GGUF format. So now you can see it's right here in this drop-down menu. I could, of course, filter if I had loads of models downloaded, but I only have these two right now. And I can just select which model I want to talk to and then start chatting with it. And so I will ask it a real question this time to tell me about dogs. And so you'll see that it's going to take a second, but this is running now on my machine. So this is a very similar chat that you would have maybe if you went to OpenAI's chat, except that this model is just running locally and none of this data is being sent to anybody. Like this is all within my system. And yeah, this is a perfectly coherent answer when asked to talk about dogs. And I could continue this chat, of course, by saying that I want it to tell me about poodles more or whatever. And no one would see that I am very curious about poodles.
Just to put a little bit of additional color, because this is just so stunning. This is absolutely on the level of ChatGPT, the Llama 7 billion parameter. So and ChatGPT itself is 175 billion is that right? 175 billion parameters? Losing track now. So this thing is 7 billion. So much, much smaller. You'll be able to download it and run it on your local machine and have ChatGPT on your local machine. With other models that are larger, like Mistral, Mixtral, you have to have beefier and beefier machine, but now we're getting stuff that can like begin to touch some of the capabilities of GPT-4. So this world is changing very, very rapidly, and be able to run this locally on your machine, mind-blowing. And I'll stop interrupting.
Question?
And I mean, with this running locally, what kind of things would I need to be mindful of if I wanted to deploy this on, research data, PHI, PPI, like the different, I think I said that wrong, but any like personal, proprietary, anything like that, is this totally locally and safe to do that on?
Yes. Well, so yes, I mean, LM Studio does say, but I think that truly, I mean, I don't think they have any way of accessing any of this. I think the whole thing is offline, that 100% of what you do within LM Studio is just on your own computer, that you could be totally free with whatever you want to feed to it and use, and it would all stay, like the data is never moved online anywhere at all. It's all stays within your computer system.
You could run this on an air-gapped machine if you wanted to. Download everything.
Yeah.
And then run it air-gapped.
Any other questions about this so far? Okay, awesome. Oh, yes.
So what are some of like the limitations with this? Because it seems really, really great, but like then begs questions like, then why would people sometimes pay subscriptions for like better AI? So like what are some of the limitations with this?
I mean, I think that the first limitation is probably just in the model that you have access to. So, I mean, this is a great model, but like Jesse said, it's maybe only some models that you could run on like really better personal computers that could get close to GPT-4 performance. So if you felt like you really needed GPT-4 performance, that would be a reason that you kind of feel like you really have to go to GPT-4 instead. Or context length, like if you wanted a model with really large context length, which a lot of times only kind of these online only versions of these models have this like enormous context like 100,000 tokens or something, that would be a reason. But yeah, I mean, if you wanted relatively simple chats and it was important to you to keep it offline or important to you to avoid a subscription service, then in a lot of ways, this might just be sufficient for your needs.
And the other thing to keep
Gotcha.
in mind
Thank you.
with this, these are going to be less capable. They're not going to, GPT-4, is great at programming. It can do very complex things. These models are going to be less than that, but you can get better than 7 billion, and the later models are getting better and better. Also, with OpenAI, for example, you do have the easy, and we'll see this on Friday, we'll see this tomorrow, easy way to create what are called custom GPTs. There was a question in the chat that, can it use tools like web search and things like that? That's another thing. Some of these models are tool users, some aren't, but that infrastructure still needs to be developed to run those things locally. So right now you're able to run just the models locally, but not all of the other things.
I also have a question.
Mhm.
On the topic of storage space on my computer, because some of these models can get really, really big. I have tried to play around in the past with Code Llama. So like, let's say this, I have Code Llama 7 billion on my computer. If I want to try the same model on LLM Studio or LM Studio, it's essentially going to just download another copy of the same model, right? And so both of those, I mean, they're like them being replicas of each other. It would just be doubling the consumption of space on my machine, right? Am I right about that?
Yeah, if you downloaded one of these model files
Yeah.
somewhere else, like in some other directory that this is not, that is a great question. So I think yes, but I honestly am not positive where on your computer this downloads the models to, and if you could just point it somewhere else, you know what I mean? Like,
Yeah.
because you could imagine a situation where you just decide you want to have like a models folder on your machine, and you'll always put models in there, and you just point this at that, and you point whatever other code you would potentially use at that, but
Yeah,
I
it's sort
honestly,
of about economizing because like I only have so many gigabytes.
right. So like, yeah, you wouldn't want to like 2 10 GB files that are the exact same thing for no reason.
Yeah.
Yeah. Yeah, I don't know enough about changing where this downloads to answer that question, but it is a really good one. And I would be curious to see how much control you have over where these downloads go. Okay. So then another kind of nice way to interact with these models is through this local inference server. So a chat function is amazing, but sometimes we want to kind of use use models more programmatically. So this is going to do something that's pretty much exactly like the OpenAI API calls, where you would be sending out, a Python call that is going to send something to the OpenAI servers and get it back, except this is going to model that exact same structure, but make the call to your local version of the model. So you can take a locally running model, start this server in LM Studio, and then move on to write yourself some Python code that simply calls the model that's already running on your machine, so that you can still interact with it through Python, but without, again, ever needing to do anything online. So here you can see that if we just hit start server, so again, we're going to choose the model up here. I'm going to keep this one. We can begin a server, and so it's going to open up the model on my machine. And then we can take, here's just an example piece of code. Okay, and the server is started, and I will, sorry, I should share my whole desktop instead of having to switch windows so often. But if we go here, this is just a Jupyter notebook that I have opened on my local machine. So again, this is all just within the context of my current computer, but now I'm interacting with Python via a Jupyter Notebook also on my local machine. And I can just point that this is where the model is opened on my computer. This is where I'm running the server. And I can interact with this model like I'm making an OpenAI API call to the model, except the model is running on my machine. So this gives you a lot more flexibility in how you interact. You don't have to just interact with it in this like chat kind of way. I could write this chat bot into a whole Python program and do whatever I want and still have the confidence that the model itself is running on my machine. So I think that somebody asked a question about using the internet, and this would be an option of how you could, in here, in the code, go grab information you need off the internet, bring it back, and then send it to the local running version of your model. And so the model stuff is all still happening offline, but you have that added step where you went to the internet, but only in Python. So like the model is still entirely offline that way.
And I'll mention we'll be touching on the framework that's the most popular framework to build those kinds of solutions, which are called LangChain. So we'll be touching on that on Friday. There are a lot of good resources for learning LangChain. Plus, we'll probably have some additional opportunities and workshops. Also know that if you're interested in this stuff and you want to develop this further, remember that we have our AI Fridays at 10 to 12 on Fridays. Not this Friday, but starting next Friday. So we'll send out information about that.
Yes. Yeah, so just I think that is all that I wanted to talk about with regards to LM Studio, but I'll open it back up here to just see if there's anything else to talk about. But yeah, just like, oh, and then here, yeah, the final tab is just that you can see kind of all of the models that you have in one place. So I guess that this is actually telling us where, to answer your question, Carl, this is telling us where it's downloaded the models to, and you can go ahead and change where you download models to. So you could make, it looks like some just shared folder on your computer where you always download models to that way. Okay. So yeah, LM Studio, like I said, is kind of, I think, by far the best way to interact with these models in this kind of era of like, there's a lot of them and they can be kind of confusing. But I will just kind of point out two other resources maybe to look at. So Hugging Face is, we mentioned the bloke repository is a great place to just kind of browse models. So all of those models that we saw on LM Studio, I can see here. The bloke is not the only place that LM Studio looks. This just happens to be an incredibly popular repository for storing all sorts of different quantizations and organizations of all of these models that makes it really easy for people to grab. But we can look at models that exist here and kind of browse like how they're formatted and all of that type of stuff. So just for your knowledge, Hugging Face is a really great resource where people post all sorts of transformer models. And it's a great way to just kind of see what's out there. You can, maybe this is a little bit to get into, because I don't want to like overwhelm you with like a whole bunch of different code ways of doing these things. But it is possible to, through Hugging Face. Hugging Face is also a Python library. So the Hugging Face team has made a Python library to allow you to interact with Hugging Face via Python. And you can also grab these models directly off of Hugging Face and use them through a call like this through Python, but using the Hugging Face package to interact with them. So that's just another potential option. If you're really excited about interacting with these via Python, that's another way to interact with them via Python rather than necessarily opening a server and doing things that way. And And then I just feel like I would be remiss if I did not point out llama.cpp. This was kind of the GitHub that started it all, if you will. Like a lot of ways now to run models locally is built off of llama.cpp, which is a team of people who worked to move llama into a easily runnable on local machines way of doing things. And in their GitHub, they do have just a lot of really good information, and they explain how you can get and run llama.cpp just kind of as its own thing on your computer. So this is just another option. It is by far kind of the most, I mean, it's not complicated, but more complicated than these other things that have kind of built on top of this. But I just feel like I have to mention it because they kind of, a lot of work you'll find is this has this at the underlying of it. So really just some great work that was done here and has made doing this local inferencing so easy. But yeah, I think that is all that I have to talk to you about local inferencing. If anyone has any final questions about what I've shown here. Yes.
Yeah, I have a quick question. So that was really great. If I wanted to upload a PDF, what would be the best way to, well, if I want, instead of doing prompts, if I want to prompt a PDF, I really like Claude because it just lets you do that. And so, yeah, could I do that in LM Studio or or would I have to like code something in Python to do that?
Yeah, that's an excellent question. I think right now LM Studio doesn't have anything that will support uploading a PDF on their end. So I think this is perhaps another instance where, yeah, maybe LangChain, which again, we haven't quite talked about yet, but we will reference, is maybe something you would want to look to for that. But I think that you would have to do some amount of coding currently to get that pipeline working with LM Studio running in the background.
Awesome, thank you.
Any other questions? Yeah.
Hi, Abby. So I was wondering if you're working exclusively on clusters rather than your own local machine. Uh, I guess it's just better to download the models in the cluster rather than having LM Studio. I guess LM Studio is only meant for, I don't know if you're working on a local machine, or is it still possible to use LM Studio within the cluster and get some benefit out of it?
Yeah, it might. Well, yeah, I guess it would depend on the cluster. I mean, with Acre specifically, I don't know if there would be a way to run something like LM Studio on
Yeah.
Acre.
You're probably going to be down to Llama CPP. Yeah,
Yeah.
you probably are back down to that level.
Mhm.
Yeah.
Okay.
Yeah.
Okay. Well, then if there,
Let me,
yeah.
Abby, let me ask you, are there multimodal models that are available through, I haven't seen them.
Yeah, that's a great question. I haven't
Available
seen,
through specifically through this nice interface.
yeah, I have not seen either. I think it's very chat oriented
Mhm.
right now.
Yeah.
I mean, they are currently working on stuff, so maybe they're going to implement it. But I think right now, yeah, it's all about chat model.
Yeah.
Okay. Well, then I will turn it over to you, Among.
Excuse me. All right. So I will be talking about how we can take one of these local models and fine tune them. And I'll also talk about a couple of different ways that you can go about that. There are a lot of different approaches to this. I will be talking about one of the most simple approaches, just to kind of not burden you with a lot of code. But this is a modification of an out-of-the-box notebook that Meta provides to you if you were to download Llama 2 from. So let me share my screen. All right, can you see my Safari window?
Yes.
All right, perfect. Cool. So what I'll be talking about is parameter efficient fine tuning of Llama 2. So as you kind of might have heard, that fine tuning these pretty large models is usually computationally extremely expensive, and doing sort of a full fine tuning from pretty much across all the parameters will require GPUs that you will likely not have at home. So you'd need something like an A100 or probably multiple A100s linked up together in order to really do a full fine tuning of even a 7 billion parameter Llama 2 model. So what a lot of researchers have come up with is this concept of a parameter efficient fine tuning of Llama 2. So I will put this notebook link in the chat. You can follow along. You may not be able to run it. The couple of caveats when it comes to running this is that you will still need an Ampere GPU connected. So this is running on Colab, and I'm paying for Colab Pro. So I actually have access to an 80 gigabyte A100 right now. So I can actually run this. But if you aren't paying for that, out of the box, I think you get access to like a T4 GPU. Unfortunately, even though that is a powerful GPU, it just won't run this specific code because and I'll talk about it a little bit, but parameter efficient fine tuning uses a lot of new technologies that just don't work on old GPU architectures. So pretty much to get started, what you'd need to do is go to Meta's website, which would be this right here. It's just their kind of start page, and then they'll tell you how to get the models. You need to visit the Llama download form, which is pretty much just a Google form. They'll give you access to it. They'll send you an email with instructions on how to download these models, and then you'll have access to the 7 billion, 13 billion, and 70 billion parameter Llama models. And you can download those locally, and you can kind of work with them. So what I have done is I downloaded the 7 billion parameter model and I uploaded it to Google Drive so I can kind of use it entirely on Google Colab and not have to run it locally, because I'm using a pretty old MacBook Pro, which just will not be powerful enough to run any of this code. So before I kind of jump into the code, I wanted to talk a little bit about what fine-tuning a large language model really is. So basically what it is, it's involving adjusting model parameters so that it performs better on either specific tasks or specific types of data or specific domains. And the most common approach, and the one that we'll be seeing today, is something called instruction fine-tuning. So basically what that means is that your data set that you're going to train on will contain a bunch of prompts, something like, explain Newton's laws of motion in simple terms, and it will be followed by an instructive response. So it'll be followed by exactly the kind of response that you're expecting to see from Llama. So basically, it'll be a lot of these pairs of instructions and responses so that over the training process, it basically learns exactly what you want it to act like. Another approach is reinforcement learning from human feedback. This is a lot more involved, but it involves using human feedback to guide the model's learning. It's fine-tuned on a data set of very similar examples, just like instruction fine-tuning. But here specifically, it's human trainers have kind of depicted what the desired output is, and then it goes through a process of trial and error and more human feedback. It's sort of like a cyclic loop until you kind of refine the responses to exactly what you want them to be. It's instruction fine-tuning with a lot more steps, simply put. And then finally, and the most easy really way to kind of fine-tune these models is prompt engineering. While it isn't technically a fine-tuning method in the traditional sense, because you're not really changing weights of the models, it is a really good way to get the model to elicit a response that is desirable. A lot of methods like zero shot or few shot learning is essentially what happens during prompt engineering, where you could give it, again, these pairs of prompt and response and prompt and response, and then it tends to learn very quickly in context exactly how to respond. So if you are looking for something that the model is generally capable of doing, but not producing exactly the right formatting of response that you're looking for, you can definitely give prompt engineering a go. And that's proven to be very, very useful for a lot of different applications. And that's primarily what my projects have been in the last year. And they work really, really well without a lot of overhead and a lot of computational power. It just happens all in context, and it's absolutely amazing. Any questions so far about just the intro to fine-tuning before I kind of jump in further? All right, and feel free to just unmute and interrupt me. Happy to answer any questions. So taking a little bit of a deeper dive into parameter efficient fine-tuning, basically what this is it enables the efficient adaptation of a large language model to various downstream tasks and applications without really modifying all the parameters. You just modify a very small percentage of the parameters, mostly because doing a full fine-tuning is very expensive. It requires very, very big GPUs. And it's just generally not accessible for the average person. So PEFD only fine-tunes a small number of parameters and reduces not only the computational cost, but also the storage cost, because you don't really need to now save these massive checkpoints. You're just really saving small training checkpoints. The method that we're going to be looking at today is called LoRa, which is low rank adaptation, and it's proven to be one of the best PEFD methods out there. Basically, what LoRa does is that it introduces these small trainable sub-modules within the transformer architecture. You freeze the existing pre-trained weights, and then you inject these trainable rank decomposition matrices into each of the layers of the transformer architecture, which allows you to pretty much fine-tune only those injected matrices and not everything else. So it reduces the number of trainable parameters by up to 10,000 times and the GPU memory by at least 3 times, if not more. And it performs pretty much as well as fine-tuning the entire model. This is a very, very high level explanation of LoRa, so it really simplifies it. But if you want to kind of do a deeper dive into exactly how this works and the math of all of this, here is the archive paper on that introduced LoRa. And this is a really nice explanation of LoRa that somebody put online that kind of simplifies it a little bit better. And specifically, I'll be using a modified version of LoRa called QLoRa, which uses 8-bit quantized versions of these models. So basically a smaller version of these models. Instead of saving these models as full floating point numbers, you're kind of using these quantized 8-bit versions of the models. So the first thing that you really need to do is download these models and save them somewhere. So I have the models in this Google Drive folder called 7B. And this pretty much, this consolidated .pth file is what the model is. These are all the weights. It's 13 gigabytes just for the 7 billion parameter model. So still pretty big, but I have it saved to this specific directory. And the first thing that you need to do is convert these weights into this specific Hugging Face format because we'll be using the Hugging Face trainers. Because right out of the box, Hugging Face has some really, really nice libraries that make all of this a lot simpler to do, and you don't really need to code all that much in order to do a full parameter efficient fine-tuning of the model. So this is just running a bunch of bash code. It's taking that file that I just showed you, and it's converting it into a format that works with the Hugging Face trainer. And this takes about 7 minutes to run. And then I am loading the tokenizer for Llama. It's important that whenever you're fine-tuning any large language model that you use the right tokenizer and the right tokenization scheme. And I'm also just loading up the model with the model ID that I specified here. I'm saying that it's the 8-bit model, and I'm saying that it uses the float 16, which is specific to an Ampere GPU, the A100 specifically in this case. And then I can print the model and see that this is kind of what the structure of Llama looks like. And it'll be important to kind of look at this in just a minute. So what we're going to do...
We're going to come back to that, Umang, just because that's fascinating to me. Well, you remember at the very first day when we looked at all of that graphic that we could sort of zoom in and zoom out of? That's what that is. So this is the text version. This is the actual description of that architecture, looking at the architecture for the transformer right here. Remember when you had the different layers? Well, those are all the different layers. They're just, 32 Llama decoder layers. And, it's all described right there. This is the text version of what you saw visually on the very first day.
Right. And the most important thing to really look at here are these 8-bit linear layers, and I'll get to why that's important. So what we're going to do is essentially fine-tune Llama to 7 billion parameters to be able to summarize a bunch of text well. And we'll see why we're going to want to do that. So what I'm using here is the SAMSUM dataset. This is a pre-processed dataset that's available off of Hugging Face.
Can I interrupt one more time? Could you describe that task again? So currently, Llama, in its current form, this version of Llama that you're working with, does not do a very good job with summarizing.
Correct.
Is that right? So you say summarize the following, and it just gives you back the same thing.
Right.
So what you're trying to do is you're going to be training the model, and so it has the capacity to actually summarize, where it did not have the capability of summarizing before.
Right.
So that's kind of the level of kind of training that we're talking about. It's just not like, oh, updating it so it knows more things. You might be training it to give a brand new capability to the model that it did not have before.
Right. And so we'll see an example of this here, but the data set that I'll be using is SAMSUM. It's just basically a bunch of conversations and their summaries. And it's, I think, 15,000 pairs of examples. Oh no, 41,000 pairs of examples. So here's an example of how Llama currently works. So here's a dialogue. This is from the SAMSUM data set. This is from the training set. So conversation between A and B talking about getting a puppy for their son. And so I'm saying summarize this dialogue and then summary. And then I give that to the model. I send it to the GPU. That's what's saying 2 CUDA so that it does it a little bit faster. And then I pretty much run it and I say summarize it. And as you can see, it's not quite summarizing it. It's basically spitting out exactly what we gave it before. It doesn't quite understand what summarization is. It understands the language, but it does not understand the task. So we're going to fine tune it so that it works better for this specific task. And so we're going to now prepare the model for parameter efficient fine tuning. So we're going to be using LoRa. And there are a couple of different parameters that I'll talk about, but this is again, very, very simplified version of LoRa. We're not really getting into the nitty-gritty, but these are kind of the basic parameters that you're going to want to set if you're just doing a very simple PEFD on Llama. So the first parameter that I want to talk about is R. This represents the dimensionality of the updated matrices that you're going to put in. A value of 8 basically suggests that the matrices will have a dimensionality of 8. Higher values capture more complex relationships, but will also require more memory. and more computation, and lower values will lead to simpler representations, so it might not learn as well. But to start off, I've seen in most papers, they say 8 is a good place to start. So we'll start with that. LoRa alpha is a scaling parameter used within LoRa. 32 indicates the scaling factor that's going to be applied during certain operations. And the choice of LoRa alpha depends on how much you want to scale the updates during partial evaluation. Again, I might understand you, this doesn't really mean all that much to you, but I would definitely recommend you go read the LoRa paper. This is a fairly complex thing that it's doing. Target modules. So this is where that kind of printout of the model becomes important. So these are the sort of focus of the LoRa method and where the scaling will be applied. Here you can see I'm specifically calling the Q projection and V projection. If you go back to what the model looks like, these are the layers. So this specific 8-bit linear layer and this specific 8-bit linear layer, this is where I'm applying LoRa. From the paper, I read that the most critical hyperparameters of LoRa is how many adapters are used, so that dimensionality, and then the fact that LoRa is applied to all the linear block layers. So if you were to apply it to all of these Q, K, V, and O projections, it will lead to a fine-tuning that is almost as good as a full parameter fine-tuning. So currently we're just doing it on these specific 2 modules. But if I wanted an even better fine-tuning, I would put all of those in there. And again, if you just want to figure out which of those layers you want to put it on, you just print the model and then look for the layers that will be labeled linear, or in this case, 8-bit linear, because we're using a quantized version of the model. And then LoRa dropout is, again, a regularization technique, ranges from 0 to 1, and 5% regularization is generally a good place to start. And you can, again, increase this or decrease this depending on how well your model fine-tunes. And then task type is going to be causal language modeling. So here I'm just saying causal LM. What that suggests is that the model is designed for the specific task where it's predicting the next word in a sequence based on previous words. But in terms of specifically the parameter efficient fine-tuning configuration, that's it. This is all you need to do. This is the configuration set for LoRa. And then you're just going to prepare the model for quantized training. So there's a method in the transformers package that does that. Then you get the PEFD model, and then you can print the trainable parameters. And here you can see that the total number of parameters is just about 7 billion here. The trainable parameters based off of our PEFD configuration is only 4 million. So we're just, the trainable parameters is only 0.06%. You would think that that's not much and it's not really going to do much, but it's apparently enough. And you'll see why. And then this is Meta's code. So they do define an optional profiler. Basically, this allows you to kind of, while it's training, get a little bit more information about what's happening as it's training. It allows you to make a couple of different decisions. You know, if the learning, if the model is just not training, this will allow you to kind of stop training and not waste time. So a profiler can be very, very useful, but in this specific example, I've set it to false, so we won't really be getting into the details of that. I'm also here creating a couple more configurations, saying the LoRa configuration is the one that we just created above. The learning rate is 1 to the -4 or 10 to the -4th, the number of epochs, steps, batch size. This is all kind of going back to just the basics of how you would kind of train any deep learning network. And then after that, it's just pretty much, let's fine tune the model. So again, you're going to give some training arguments. You're going to say where you want to save the checkpoint to. You're going to say if you want to overwrite, if stuff already exists there. BF16 specifically refers to the kind of floating point bit. So BF16 specifically works only with Ampere GPUs. So this, you would say, you would put this as false if you're using not an A100 or an A10. because only Ampere GPUs apparently are able to do that kind of or deal with those kind of floating point numbers. And then logging steps so that you kind of see what the training error is at every 10th step.
And Umang, just a quick question. Could you, like, for most tasks, do you think you could just like take this template code and just
Yes.
run with the parameters? And did you actually change the parameters all that much, or did you just say, no, I'll take the defaults?
I changed one or two things here and there. Sometimes I kind of made this false because Google Colab will refuse to give me an A100 sometimes. And I changed the logging steps to 10 so that it doesn't print every single training loss. But pretty much you can use this out of the box. I've used it briefly to fine-tune Llama to work with medieval French, and this out of the box works. So you really don't need to do all that much thinking when it comes to this. You can take this template and really run with it.
And the other thing that I'll make again is, if you're interested in doing this, remember our AI Fridays, 10 to 12 open door.
Yep. And then pretty much, again, this is just defining the profiler again and saying that use the profiler while training, and then trainer.train just starts the training. This took about an hour and 7 minutes on this A100, and you can see it had 380 steps, and the training loss kept going down as you would expect it to. And so about an hour later, the training was done. I saved the model checkpoint, a directory in Google Drive, and then I called the model again on that same example that we saw earlier. And I said, okay, summarize this dialogue. The dialogue is there. And then the summary: A wants to get a puppy for his son. He took him to the animal shelter last Monday, showed him one that he really liked. He wants to name it after his dead hamster, Lemmy. So just fine tuning on 0.06% of the parameters of the entire model got you this far. And it only took an hour on an A100. Yes, A100 is a very difficult machine to get your hands on, but $10 a month on Google Colab will get you that, which is absolutely awesome. And also, if you are a Vanderbilt affiliated person, we also have DGX A100s at the DSI. We have 4 of them. And if you're really wanting to do something huge, we have up to 1,300 gigabytes of video RAM when you link all of them up together. So you can really do some extremely powerful stuff.
So even on $10 a month, I mean, so you can think about the type of research that you could do here. So on the one hand, you have OpenAI and you have GPT-4, and it is like, you know, jack of all trades, right? Master of maybe a few. But here you have a much smaller model, but you could absolutely do fine tuning so long as you have training examples, and that's the key, is have training examples for you to train the model on. But then you can train a smaller model, which is not jack of all trades, but you could make a master of one or of a few. So if you have a specific defined task, you can absolutely train a model much smaller to be a master of that particular task.
Right. There was a question in the chat about what exactly the profiler is. The profiler essentially allows you to keep track of the training a little bit better. It'll print out more than just the training loss. It'll give you a little bit more information about exactly how the training is going. I've actually never used it, so there's not really much more I can tell you about it. But apparently it gives you the ability to stop the training based on certain specific parameters that take place. You know, if the training loss isn't quite going down the way that you expected it to, it can stop the training midway, or it can maybe even change parameters off LoRa midway if you needed to. But profilers can be pretty powerful if you use them correctly. Yes, there's a question, Michael.
Yes, thanks so much. This is really interesting. Since I am very new to this, and it seems like what we are doing is we're taking natural language processing and we're using a large language model to introduce AI in terms of how it functions. Am I following correctly, or am I missing the boat? I'm just looking at the literature that's out, and I recognize this is ahead of the literature. I'm just trying to figure out, how do I describe this as I'm attempting to hang it in my mind?
I like to just think of it as, these models have a really good understanding of the English language, but sometimes they don't quite understand tasks. So summarization is a task. Translation of one language to another is a task. It might have all of these representations of different languages and concepts in there, but it doesn't quite understand how to respond to a specific type of question. So basically what you're doing it is giving it examples of how to respond to a specific type of question. And then over the training process, which is about 40,000 of these examples, learns that, okay, when I'm being asked to summarize something, this is exactly what I'm aiming for. And it kind of learns to do that whenever it's asked. I don't know if that exactly.
Yes. Yeah, that is helpful. Yes, that's very helpful.
Jesse, do you have anything else to add?
I might say sort of natural language processing is a much older term, and it's not quite orthogonal to, but it is definitely at an angle to what's happening with large language models, right? So large language models can do the things you used to have to do with natural language processing. We can also do a host of other kinds of things, problem solving, just like you saw with summarization. With this, you're taking a large language model, in this case, a 7 billion parameter llama model, and you're doing additional training. That additional training could be of any kind of sort. You could train it on a new language, just like with Umang did before with medieval French. So it didn't know medieval French, it knew other things, but he did additional training so it could know and work with different dialects of medieval French. You can use it to train it to do new types of tasks, like in this case, like learn how to do summarization. You can also do fine tuning, and so it responds differently. It's more like a chat bot rather than just spitting back answers. You might even do fine tuning, and so it would stay away from certain subjects or handle subjects in a particular way, which is what you find a lot of these models are that are offered by companies that they've done. Sometimes they do that with a different type of training, but with this type of training, all those are possible, right? So here's natural language processing over here. It's concerned with certain things, but now you have this entire large field that you can cover with large language models, and being able to do fine tuning and parameter efficient fine tuning gives you the opportunity to train your own model to do specific things.
That's really, really helpful. I read an article this morning. I won't take any more time, but I'll come to the time on Fridays. Does that begin next Friday?
It begins next Friday. That's right.
Perfect. Thank you.
And there's another question in the chat. Is there a sort of a list or menu of all the fine-tuning options and capabilities for this model? It really depends on, what data you have on hand. So if you have translation data, you can kind of create a data set that works for that. It's pretty much up to you. Yes, there are limitations. This model will not do well. And I tried this actually. I tried to fine tune it so that it would understand Hindi better. It does not. It does not understand Hindi only because the tokenization scheme that Llama uses does not have representations for Hindi characters. So basically it's breaking each of those down into like their UTF-8 formatting. And so, just my name translated to Hindi would be, instead of 2 tokens, which it is in English, is actually 5 tokens or 10 or 12 tokens in Hindi. So it's important for you to kind of understand what the bare minimum capabilities of the model are, and you can kind of play around with that by looking at the tokenizer. You can take the tokenizer and you can give it any text and ask it to tokenize it, and then just count the number of tokens it takes that one sentence and breaks it down into, if you're specifically looking at language. And so there's a variety of different ways that you can figure out what this model might be capable of or not, but usually kind of just inferencing on the model like we did up above to see that, oh, it doesn't do well on summarization right now, kind of gives you an idea of what you can and cannot do. Generally, I've seen languages or translation from one language to another is probably the hardest thing for it to do if it doesn't already have those representations. But for like tasks like, writing poetry or or just any sort of creative task, or asking it to think like or speak like a chatbot. All of those things, if it understands the English language well, it can probably do it.
Thank you so much.
Yeah. Other questions?
Could you put the link to these two papers you mentioned in the chat if they're not already in there?
They are, but I can also put them in the chat once
Okay.
done sharing. So before I kind of wrap this up, I did want to talk about a couple of more things. As I mentioned, that this is sort of an out of the box, very simplified training. So while it is still very powerful, as you saw, only 0.06% of the or fine tuning, only 0.06% of the parameters led to a very, very good outcome. There's a lot more you can do. Sometimes even that 1 hour might be too much. Imagine if you're trying to fine tune on a much, much, much larger data set. You're going to want to use something called Flash Attention 2. It's a faster version of attention. And Jesse can talk to what exactly that means a lot more. But Flash Attention 2 is restricted to Ampere GPU, so you will need an A10 or an A100 GPU, but that significantly speeds up the process. I tried it once, and I think instead of an hour, it took about 20 minutes. So it really becomes a lot faster. Again, also LoRa has several other parameters that you can modify. So definitely take a look at the LoRa paper to learn a little bit more about it and really understand what it's doing. There are also easier ways to access this model. As I said, I downloaded that 12 gigabyte version of this model and then uploaded it to Google Drive, which took absolutely forever. But Hugging Face has collaborated with Meta to provide online access to these models through the Transformers library, which you can do so you won't actually have to download the model every single time. It only downloads the parts that it needs. And it also has dedicated libraries for PEFD, part of which we actually used here, which allows for seamless implementation of these methods. And finally, custom data. So I use the Samsung data set here, which is a pre-processed data set, which takes care of, I would say, almost 90% of the work that you need to put into this if you're trying to pre-train a model for a specific task or something. A majority of the setup really is getting the data into the right format for training. And the format for training varies from model to model. So Llama specifically requires its data to look like a specific format if you want to fine tune it, which sort of looks like this right here. So it'll be hashtag, hashtag, hashtag instruction, gives the instruction, hashtag, hashtag, hashtag input, the response, and then the response. So it needs its training data set to look like this. So an example training item would be an instruction, which is use the input below to create an instruction, which could have been used to generate the input using a large language model. Complicated, but the input to something like this would be the names of these two people, and the response would be classify the below Nobel Prize winners or whether or not they received the prize in 2022 or 2021. So this is kind of what the data set should look like. And so if you're doing translation, it would be, you know, English text and then medieval French text. And then you can kind of just ensure that your data has this formatting. The hashtags are pretty much the important part. And then you can just replicate that across your data set, get your data set to look like that specific formatting, and then you're kind of there. And then I have a couple of different resources down here. There's OVH Cloud Llama fine-tuning demo. This is really, really good. It also does fine-tuning on a single GPU and uses QLoRa. Hugging Faces Llama 2 page also has a really good set of information on parameter efficient fine-tuning. This is another demo that works really well. And then if you cannot get your hands on an A100, you are able to fine-tune Llama on a single RTX GPU. It is going to be a lot slower, but it will work. And this person on Medium was actually able to do that. I haven't been able to actually implement it, but mostly because I don't have an RTX GPU. But this is also a really, really good alternative. And that is all. Questions?
There's a question in the in chat from Alyssa. Can you give an example of the format for training using unlabeled data or or does that so Alyssa, you might want to ask.
So unlabeled data, no, I actually wanted to try and do something like that. And it pretty much your best bet is this sort of instruction fine-tuning where you have an instruction followed by a response and then sort of these pairs that it trains well on. I really haven't come across a good way to really use unlabeled data. I think if you're trying to use unlabeled data, you might want to go down the route of training from scratch. But at least that's kind of what I found.
So are you able to do training using causal modeling? Like causal modeling training task using QLoRa?
As far as I know, no. It really needs to be sort of this formatting instruction like input output pairs.
For at least or at least for this for the pre-prepared llama that but they're and as I was going to ask you about sort of other approaches, like is there this nice infrastructure of like built solutions for like Mistral yet?
Mistral, yes. It really depends on if they really want to give that to you. I know Meta for all of its models so far gives you these notebooks and examples of how you can fine-tune their models. Not everybody does that. For example, Bloom really does not have all that much information out there on how you could do this sort of fine-tuning. But and GPT 3.5 also uses a very different approach, but you can also fine-tune GPT 3.5 using OpenAI's methods that they have. But it does vary a lot from model to model. So if depending on the model that you're trying to fine-tune, you should be able to find some information on how to go about it.
So one other thing that I'll mention here is that LoRa and QLoRa is just one approach for parameter efficient fine-tuning. It's one that's found a lot of success. So there are approaches where you can do this type of unsupervised fine-tuning, but it might require a different approach. And it may require training of the entire model. And just be clear that that's not a showstopper. That just means if you need to train the entire model rather than using a parameter efficient method, it means you're probably going to need to run it on like the full DGX. But we have compute grants for that, so we can talk about that. Either one of our DGXs or the four sort of all yoked together. So that's possible to do. I think this would be a great opportunity. Come by the OpenAI. I was come by our keep on wanting to say OpenAI now. Our AI office hours. And we can discuss more in depth about what's possible, because it is a quickly evolving environment, both and not just on the solutions that use parameter efficient fine-tuning, but even on the development of new types of parameter efficient fine-tuning methods. Like the theory itself is developing as we're speaking as well.
All right. And that is all I have. So I'm going to hand it over to Shara.
All right, fantastic. Coming up, we will talk a little bit more about the different things that we can use now that we know how to do parameter efficient fine tuning. We're going to quickly take maybe a 10-minute break. So come back at 12:25 CST or C whatever T Central, and then we'll talk more about that. See you then. All right, I think we're done with our break and it's time to mosey on back and chat a little bit more about what we can do now that we know how to use parameter efficient fine tuning. All right, let me just check and see and make sure that people are coming on back. All right, fantastic. All right, great. So again, my name is Sharo Bell. I'm a senior data scientist here at the DSI. If you have any questions, please feel free to just drop them right on in the chat. The conversation here has been fantastic, and I know that this is a really unique topic that really doesn't have a lot of online training. So anyone who would like to chat more about this, please feel free to pipe in. I really love the conversation thus far. So again, we're going to be talking a little bit more about the types of training that go into chat models. So on Tuesday, we talked about transformer models, specifically these decoder models that are generative in nature. On Wednesday, we talked about models, the different models that are out there in terms of their size, in terms of their training, what they can do. Today, Abby told us a little bit more about LM Studio, and we learned that, boy, there are a lot of different models that they can train from or that we can use and we can train. And they have all of these different annotations as to what kind of model that they are and what kind of quantization. How can we try to parse those things out? And again, Umang talked to us a little bit more about once we choose a model, how can we go about training it to do the tasks that we're actually after or make the changes that we need. And he showed us how we can do that with parameter efficient fine tuning. So now we're going to, I would say, back up just a little bit and discuss how we even got to the point of the chatbot that is ChatGPT, GPT-4, whatever you want to call them, specifically ChatGPT 3.5, that's neither here nor there. But chatbots like Bard, how do we go from these quote unquote LLMs to these chatbots? And so that's what we're going to discuss, the different steps that have been taken in order to get here, namely because that will also help you to discern what steps that you might need to take if you would like to train an LLM further, or if you are actually beginning from some signal-based models that no one has even created before. So before we do that, are there any questions? All right, fantastic. So a little preface here. So I'm going to present some slides. I was not able to push them to GitHub the way that I wanted, but I will try to drop all of the links that I will click on from the slides in the chat, so you'll be able to follow along as well. All right, so again, we are talking today about what happens after pre-training. So let's say that we have an LLM, so a large language model, which is what we've been talking about. There is this interesting abuse of language that goes around LLMs, where it's small models, it's big models, it's ones that have been trained in certain ways. I really wish that we could call the super large language models, like so our chat GPTs and our GPT-4s, I wish we could call them XLLMs. And I feel like we could draw that distinction, but that's not what we're doing. Nonetheless, so using these LLMs, we're going to talk about some of the different steps that Umang highlighted, namely supervised fine tuning through instruction fine tuning and other approaches for supervised fine tuning, as well as reinforcement learning from human feedback. We're going to talk a little bit more about some of the data that's needed, what it looks like, the components of human effort that are required to even just formulate the data sets needed to train these. We're going to talk a little bit less about the code. In fact, we're going to talk pretty much not about the code because Umang kindly covered that for us. And also Abby and Umang covered the PQ. So we'll also briefly touch on some of the open source Hugging Face documentation that you can use in order to kind of sift through some of the more ambiguous parts of these fine-tuning methods. And then we'll also talk a little bit about some optimizations. So in thinking about these chat models, they all started off as LLMs. So the first thing that we ever talked about in this class was about how we need to do this task called causal language modeling. And that is how we get our base versions of our LLMs, meaning that the first thing that we tend to do is have this pre-trained model or train this pre-trained model. OpenAI did it. Google has done it. They get this model that can predict the next token, okay? And so that is something that we know about. Wonderful, great. However, that's not the model that we really use. We're not using just this base model where it's just continuing on whatever statement that we have made. It's doing these additional tasks that actually make it useful for us as something more of a chat agent. And so we're just gonna just mosey on over very quickly to what makes a dialogue agent useful. This is part of a blog from Hugging Face. And it was made a little bit of some time ago, but it's still very, oh, nope, I'm pasting this in the wrong place. It's still very useful in terms of understanding the additional things that we need for our chat LLMs. So not our regular LLMs, but just our chat LLMs to actually be useful for us. So this, again, you can see this was made some time ago because it calls Anthropic's LLM or chat LLM assistant. We know that that is pretty much now called Claude, not even Claude, but Claude 2. And after this class or whenever you have time, you can take a look at some of the little bit of the older models. Something interesting is you see that ChatGPT was also referenced as something called InstructGPT in these days. That should tell you something about the kind of task that ChatGPT needed to do in order to become ChatGPT instead of LLM GPT or whatever have you. So namely, we can see that there are things that occur after pre-training. So we can see that there are a lot of data that go into pre-training these models, but then we can also see that they do things like supervised fine-tuning, which is, we'll talk about exactly what that is later. Umang is giving us a little bit of insight into what that is. You can also understand about the size of what they were using for that supervised fine-tuning. Then they talk about this thing called RLHF, which is reinforcement learning from human feedback. Not all models do this. And you can see that some over here do this, but some don't. Again, this was made a little bit of some time ago. So reinforcement learning from human feedback very much was the way to achieve certain things that we wanted to get in our chat models. But now there are some more modern approaches for that. We can see that in our chat models, we need to have some sort of safety, whether they're handwritten or not. And whenever we're using these language models, even us, as we are experimenting with them and using them, we need them to have certain qualities. So whether they are making sense about what they return to us, whether they're saying things that are actually relevant to what we're trying to get at, whether they're harmless. So if we ask them about how can I build this chemical weapon, that they need to not tell us the detailed instructions on how to do that and where to get every single material from. And also we need them to be as least biased as possible, even though that in itself is a challenge. So with our base LLMs, when we are predicting the next tokens, these are not things that we get for free. This creating the best answer of possible, this alignment in terms of being helpful and being useful and specific, these are not things that come for free. These are things that must be specifically trained into the model. So first, we have talked about how, although we start with the LLM, that does predict the next token, again, called causal language modeling. What we needed to do next is to be able to actually follow instructions. So we say, hey, can you create me an overview of, I don't know, bullet points for a slide deck that we want to create? We want it to actually begin to create that slide deck in bullet points instead of just continuing on with that statement that we had just made. So to do that, we take this step called instruction fine-tuning. And what essentially that is a data set that is composed of instructions. So you can see here as an example, give me a quote from a famous person on this topic. And then we actually get the output that we actually want. And so we have honesty as the first step, blah, 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 blah. So it now follows instructions and gives you the answer based on the task that you want it to do. So we'll get into this even a little bit more, but basically whenever you have this instruction fine-tuning data set, it usually tends, or at least started as human written instructions. Now we have a number of open source data sets that have a number of instructions, and also LLMs themselves can help in generating these instructions to train other LLMs. after we're able to actually follow instructions, we need the models to actually be safe in the way that they follow those instructions. Not just safe, but also helpful, so that they actually provide things that can help us, as well as not saying crazy things that are detrimental for society. Generally, people call that supervised fine-tuning, but to be fair, instruction fine-tuning is also like a subset of supervised fine-tuning. They're pretty much doing something similar. The point is that you have usually these handcrafted inputs where you have also handcrafted outputs. So the difference between instruction fine-tuning and what I like to call pretty much safety fine-tuning is the content of the data set. Specifically with instructions, you're trying to get it to follow instructions. With safely following instructions, you're trying to get it to actually do things beyond instruction following that are more safe in those instructions. Finally, we have this reinforcement learning from human feedback. So now that we have this model that predicts the next token, but beyond that can follow instructions, and beyond that can follow them safely, we wanted to actually we want the model to actually give us responses that we would prefer. And that is done again by these large data sets that are pretty much handcrafted by humans, but again can be bootstrapped by LLMs and created. And so these are again, these data sets that have these particular values that are associated with the goodness of any given response. We use that to train this thing called a reward model. And basically, again, we'll talk about this a little bit more, but as we're training our model, if the model gives a better response, it gets more of a reward. And so that allows it to understand that we prefer this response instead of another one. So this is reinforcement learning from human feedback. There are also other types of training that these models sometimes undergo. One is chain of thought prompting, which is exactly what it sounds like, thinking step by step. And so you can see some examples here. So all in all, we have discovered that there are lots of things that we need to do after we've just pre-trained our model. Not that we really need to do them, that have been done to create these chat LLMs. So coming back, you can see generally what has occurred. Our chat LLM benefits from all these different training steps. We have our pre-training, as we know, which is usually done by like some companies, so OpenAI, Google. If we are making some LLM ourselves, then that would be us, and we would be spending lots of money and lots of compute to make that happen. Then we have our instruction fine-tuning and safety fine-tuning, which we would like to call as a set supervised fine-tuning, where we are trying to get the model to either follow instructions or follow them safely. And then finally, we have this reinforcement learning from human feedback, where it's going to give us answers that are better or according to how humans would rate them. Okay, so moving right along. Whenever we are thinking about these different tasks, okay, so we just talked about 4 tasks. We might wonder for ourselves or in general, what kind of data and what type of tasks are needed during this training. So again, we have talked about supervised fine-tuning, instruction fine-tuning, safety fine-tuning, and pre-training. All of these things actually undergo the same type of training, which is causal language modeling. So the data that you might have, for example, for instruction fine-tuning might be an instruction, and then the thing that you want to get out. And then what you would actually put into the model for causal language modeling would be the full statement. So here you would have below, and then after that you would want to predict is. And then after you have below is, you would want to predict and. And so they're all the same approach for training, so causal language modeling. The question is, what is the data and the content of that data that you are applying causal language modeling to? So that is the majority of our steps. The second piece is this reinforcement learning from human feedback. And I do have the star next to it because, again, there is movement towards a little bit of a different way of doing this, but specifically, again, with reinforcement reinforcement learning from human feedback, our goal is to generate the best response. And so let's say that we have this prompt where we have ships at a distance, have every man's wish on blank. Thank you, Jesse Smith. Love that example. Taking it back to the first day, we might have these different answers, and we all gave different answers, right? And so someone has to choose, or some set of people have to choose based on some basis, which they think is the best answer and by how much. And so this thing right here, you can see that we have a few different answers. They have a few different rewards associated with them. Should the model choose deck, it'll get a reward of 3. And should it choose board, we'll have a reward of 6. And by doing this, this helps the model to learn the best responses according to what humans have rated these different types of answers. So by doing this, we have the model choose the best answers according to humans. And so generally, again, there are 2 kind of distinct ways of doing that right now. One is this true reinforcement learning from human feedback by something called PPO, which is where you yourself as a researcher or whomever, you must specifically develop the model which creates this reward. And it's a little bit intense. And then on the other hand, there is another way called DPO. And instead of just having like these set of rewards and an explicit reward model, you instead just have your preferred response and then a rejected response. So again, we'll talk about that a little bit more, but very clearly this data set over here for pre-training and supervised fine tuning, again, it's going to be causal language model, and the question modeling, and the question will just be the content of that data set. All right, so just taking it back to 0, just to remind ourselves about pre-training, what that looks like. Again, what we're trying to do is learn about whatever language that we're trying to learn about. We're trying to learn the semantics, the concepts, all of that great stuff. And again, we're trying to do this causal language modeling and predicting the next token. The size of that data is particularly large. We saw that here, again, when we were looking at this pre-training corpus size, and this is given in number of tokens, but really this translates to hundreds of thousands of documents. Usually this is going to be done, again, by some commercial person or company where the outcome is that we just want this model to be able to predict the next token some way that is grammatically correct and is making some sort of sense. Based on what Abby showed us, we know that there are different kinds of models trained in different ways on LM Studio, but very truly on Hugging Face. The way that you will distinguish the model that is pre-trained is it usually has base in it, or it does not have chat, instruct, LLM, or chat, instruct, or like reinforcement learning, those kind of terms. So if you see base, it's probably just the pre-trained model. All it can do is predict the next token. So we're going to take a moment and prove this to ourselves. I know that people sometimes will just think that any LLM is a chat LLM. It's just not true. On which day was it? Wednesday, we talked about Mixtral and Mistral. And so we're going to just briefly take a look at what that is like when we have a base LLM. So I'm going to put this in the chat right quick. This thing that we're looking at here is Mistral again. It's a large language model. And this whole thing that we're looking at is Hugging Face transformers. We're on one of the models, which is this one, and we can sometimes actually interact with this model. Okay, so this is something that's called the inference API. This means that you're able to sort of interact with the model and understand generally what it's going to be doing. As a side note, this thing over here is called a model card. It is essential in conveying to people what your model is, what it does, limitations, safety, environmental impact. These are pretty much essential for whatever model that you would share publicly. But regardless, we can see, number one, the example that they create and show us here is, my name is Mariama, my favorite. This is not an instruction. This is not a question. This is literally continuing the next thing. So if we do compute, this is the input and it's going to tell us the output. So we can compute. And you can see that it is really doing that base pre-training task. So it is only just computing or outputting the next part of the sentence. So let's say that we decide, I actually don't know that. And so I want to give it an instruction to execute. So let's give that a try. So this is something that we might put into ChatGPT or Bard or whatever, because we think that it follows instructions. Here, if we try to compute this, you see that actually it is just continuing it on with whatever we had just originally said. So what this means is that this model requires more training if you want it to do any kind of instruction, if you want it to be safe, or if you want it to give you back the best response. So that also means that if you don't care about those other things currently and you want to do your own kind of instructions, or you want to do your own kind of safety, this right here is a great place to start if you just want to start from a pre-trained model and do all of those extra things from scratch. Okay, so this is an example here. Again, lesson here is that not all LLMs are chat models. They don't all have reinforcement learning. They don't all have instruction fine-tuning. The base ones tend to be just that pre-trained piece where all they're going to be doing is predicting that next token. All right, questions thus far? Are we feeling confident about that? Is it making sense? Are we convinced about that? Okay, I think we're convinced. Awesome. Moving right along. Then coming to something that we probably know just a little bit less. So our second, third-ish step of supervised fine-tuning, where we're trying to do instruction fine-tuning and safety fine-tuning. Oops, sorry about this. Not right. Oh, actually, just kidding. That is right. So here we're trying to learn how to follow instructions from the user. We're also trying to learn how to do that safely and helpfully. And again, we're still on this predicting the next token. All we have just decided is that we want a different kind of data set. So again, what we have at the end of this is something that is able to actually follow the instructions. Now, I know, last thing is, if you're going to something like LM Studio or Hugging Face, in those models that are instruction fine-tuned and safety fine-tuned, sometimes you'll see something called instruct. So they're called Mistral-instruct, or they're called Mistral-chat. Chat, you have to look and understand a little bit more exactly what is meant by chat, but for sure, if it's instruction fine-tuned, it'll say instruct if that's the extent of what that is. So there was a question earlier about what the data sets sort of look like for that, and Umang explained what they tend to look like, but we can actually explore that a little bit more through, again, revisiting Hugging Face. And so we're just going to step on over to Hugging Face data sets right quick, and I will again put this into the chat. This Hugging Face data sets website is really nice. You can already see that there are tons of data sets here that one can use if they want to do their own instruction, if they want to find something specific that they want to train on, whatever have you. And so let's just take a moment and explore that. So we were just talking about instruction fine-tuning. What if we just search and see what is under instruct? So here we have searched that, and we can see some different types of instruction data sets. So the thing about this is that you do have to be a little bit careful about which ones that you pick. Not that you have to be careful, but you just have to be vigilant. Look at the data set to make sure it's what you actually want. So let's just take a moment and just like explore one. I'm going to actually look at this med tune instructions because it sounds super interesting. So when we click on that, we see something interesting. So we see this data set. You can see the examples here. You can see that we have only a train split. Often there is other splits like validation and test. If we want to look at this a little bit more in depth, we can go to the data set viewer, which is going to show us the same thing. It's just that we're going to be able to look at it even more. So here, maybe this set of instructions is this here. Your goal is to be able to blah, 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 and classify them into this, that, and the other. And then the input is this, and then it's going to say this is the output or whatever have you. If you see a data set like this, this is something that you will likely have to reformat into an actual instruction fine-tuning format, meaning that you'll need to kind of put all these things together so that you get your actual predict the next token looking sentence. So essentially you might put the instruction first and say the instruction here is, the question that is proposed is this, and then also provide the actual output that you want the model to state. Let's see if there's anything else that's good. Sometimes I just look at particular names. So maybe alpaca. All right, let's see. We could probably look at a number of these. Maybe we have the ability to sort these. So maybe we will try, I don't know, the most downloaded. Oh, interesting. So this is the actual alpaca data set. Alpaca is an open source data set of instructions. So let's take a look at that. We again will go to dataset viewer. And here, this is where we can see the actual setup of what we want our instruction fine-tuning data set to look like. So for example, you see that we have the instruction. There is no input here, but we want it to just generate some output for us. And this is the output that we want. Therefore, this is what we would actually put into the model to predict the next token. And so you can see a number of examples here. Some of them actually do have inputs. And this is generally, so this column here is generally what you would put into your. In this particular notebook or the slide deck, there are also a few, oh, that's what I just put there, self-instruct, whatever have you. There are a few other data sets that are also of interest, but again, looking at Hugging Face data sets will provide you a lot of different options for instructions based on your use case. Finally, we get to this reinforcement learning from human feedback then, okay? And again, we've already stated that there are some different ways of approaching this. In fact, there's lots of different ways, but there's two specific ways that people tend to approach this. Again, the whole point of this is just to give the best response based on human preferences. So if people, if your raters decide that this response is better than another one, then our model will learn to have this response A instead of this response B. And again, after that, we have our full pretty much chat model. Whenever you are looking at these model names and you see like chat, this is usually what is meant by chat. Sometimes you'll see this RLHF, which is meaning that most of the time it's gone through all of those steps. So in the interest of time, we won't go into the minutia of what these different types of training are. Basically, what happens is there are two different ways generally that this is approached. One is called PPO, which is something preference optimization, proximal policy optimization or something like that. And there's another one called DPO, which is direct preference optimization. And so that is kind of almost just drawing the distinction between what these two things are. Meaning that here you can see that this is just straight up, it's looking more complex than this thing over here. And there's a reason for that. This image is actually from the paper about this DPO, and you can see the comparison. This image here is essentially a simplification of this image here, and it's basically saying that you have this preference data, and so you have to create your own reward model that is going to provide you back a number, which is going to tell the model the goodness of that particular answer. And then with that, you have to do this policy update, which updates the gradient, this, that, and the other. It's pretty intense. With this DPO thing, what they've done is they've reconfigured essentially the policy into a maximum likelihood configuration. So it basically simplifies down to a classification task. So this is becoming extremely popular. If you go on Hugging Face and look at the data sets, almost all of the data sets that you currently see have two fields, and those fields are essentially three fields. One is prompt, the other one is chosen, and the other one is reject. And so we can look at that in a moment, but essentially the point is that you are choosing one particular prompt over another, prompt or response than another. And it simplifies the whole process a lot more. If you are really into doing this coding thing, there are additional instructions on Hugging Face about how to do this. Umang showed you a particular kind of trainer. The thing about Hugging Face is it's going to try to keep its interfaces for training pretty much as common as possible. So once you learn how to use one, you can learn how to use the other pretty well. So here are some instructions on how you can do that. And if you want to learn more about this direct preference optimization, you can learn more here. Here you can also see what the data set for this type of optimization is, where you just have a chosen prompt or response versus one that would be rejected. You can also see who is making these kinds of data sets. So for example, the canonical example here for DPO is Anthropic. And you can see that they have this reinforcement learning for human feedback. And you can see that they have these exact columns, which you would use for the direct preference optimization. As a side note, the thing about Hugging Face and why I'm always just talking about it, if you want to use it, is that mostly they're just going to provide you the code to do it. And then you're just going to use it and move on and have a good life. Sometimes it does take just a little bit more effort than that, but most of the time it's going to look, I mean, they put it there for you to use. See, was there anything else at the end of the slide? No. So we don't have time for you to try it yourself, but I would highly suggest, highly ultra suggest that you go and you explore Hugging Face data sets. Again, if you are a little bit light on data and you need something maybe to bolster, or maybe you're not even light on data, you have no data and you want to do some sort of instruction, fine tuning, or you want to experiment, these data sets here are ones that are submitted or contributed by companies, they're contributed by individuals, by universities. You can search for whatever you're looking for, and maybe you'll be able to complement your own data with whatever is there. In summary, okay, so we have these different steps of creating our chat LLM. Generally, we start with pre-training. That's going to take a lot of data. Our supervised fine-tuning, it's going to take less data, but still a good bit of it, especially if we are coming something that's meant for everyone, like ChatGPT. And then with our reinforcement learning, we're going to have, again, a pretty large data set when it is initially created. However, as a researcher, my suggestion in terms of choosing to develop these models, if you are doing something that has a sort of chat LLM kind of approach, so mostly if it's natural language, I would absolutely recommend starting with prompting before you get into the training component. Start by prompt engineering. Try to, create a prompt that allows the best sort of response possible. If that doesn't work in a shorter context model, move to a longer context model. Try to provide more information, use your prompting patterns, use the best practices. If that's not working, you can add reference documents. You can add them directly into that long context. If that's not working, you can also put in examples of what you want for the model to output, in addition to all that reference that you have put into this long context. If all of that is still not enough, you can move on to retrieval augmented generation, where you can upload a zip file or whatever have you of PDFs that it can look for and reference when it is trying to give you an answer or your output. If all of those things fail and you have tried your absolute best with prompting, then it may be a moment to begin to move on to your next steps of what you might do. So then so if you decide to move on to pre-training, usually the case is that your model needs additional domain knowledge. So let's say that you're working with the law, all of your prompting has just failed miserably, you cannot make it work. You might need additional knowledge in terms of domain. And so you might choose to do a little bit more pre-training. Because pre-training looks so close to instruction fine-tuning, safety fine-tuning, all that great stuff, it might be interesting to just think about it more in this space of supervised fine-tuning, where you are trying to make it output something that you actually want. So instead of just pre-training, I don't know, for just like law things, you might actually just move it closer to the space of following instructions or doing something in terms of safety, or just doing something that you're actually wanting. If you are starting with pre-training, like scratch, usually you're in a space where there's no model for you. So for example, Abby, she's working with LIGO data. There's not really a model for her to start with for all of her signal data. She has lots of data that she can use to pre-train this model, train this model, or whatever have you. This is where she would start. EEG people, this is probably where you're starting as well. If you need some different custom better instructions, guardrails, whatever have you, or you want to put in this chain of thought prompting, you might start at the supervised fine tuning. If you're reinforcement learning, if you're thinking that maybe you just want some different preferences in terms of your model output, then you might start at the very end. With the caveat that sometimes if you start with this model that is fully trained, so a full chat model, sometimes it can be challenging for after reinforcement learning from human feedback to go back steps. So instead, you might have to start with a model that is potentially does not have this stage. So start at something that is at this stage, and then do a full reinforcement learning from human feedback, adding in the components that you want for the better preferences. And that is about it. It is 1 o'clock, and so landed right here on time. We've learned a lot of things, hopefully. But I will try to provide the slide. I will provide the slide deck to you once I figure out how to put it on GitHub. And then you can learn a little bit more about the next steps of your own research. So thank you for your time today. I hope that helped, and I'm happy to answer any questions now or during office hours.
Right. Thank you all so much for that was again high speed, a lot of information. That's what AI Winter is. Thank you all so much. So let's go ahead and so let's thank all the presenters. So thank you very much for all of the effort that you put into pulling together all this information. Just so you know, each time that we make these presentations, it's like a new prep each time because so much has changed since the last time that we did it. I don't think we've ever had an AI summer or an AI winter where we're able to like just reuse all of the material. It's always new, always new. So so we're going to end the instruction part, and we're going to open up our office hours now. So thank you all. Congratulations on getting done with the 3rd day of the AI winter. We're going to be sticking around for any questions that you have for our office hours. Thank you, Sheffield. Thank you, Fenji. Thank you, Em. Thank you, Dan. Thanks, Gayatri. What questions do you have?
I have just a not it's a calendar question actually. Does a calendar invite exist for the AI Fridays? I can do it myself too, but I'm wondering if it's already out there.
No, I don't think we do. Are you thinking of sort of sharing it so people can put it on their calendar?
Yeah, like a reminder. I mean, well, I'm thinking of myself, but like a reminder
Yeah.
that this happens every week.
Right. And we're doing 10 better make sure that I have my no, I keep this on Central Time. So 10, and we're doing 10 to 12. I'll create one now. I mean, we do need a new Zoom link for it. So and I'll add you to it, Carl.
Okay.
And, it's not a bad idea. We could create an ICS out of this.
I had placed it on my calendar, so if it isn't too much trouble, I'd love to be included as well. I can add the Zoom invite to what I.
Yeah, we like to do in person, but we can do Zoom for people who are not able to make it in there. It so like Umang is remote, so we actually, you know, you'll see our little Umang robot, which is.
That's great. I'm usually on campus, so that makes it.
Oh, great. Okay, good. What other questions do you have?
Hey, if nobody has one, I'm trying not to monopolize, Jesse, but I have a couple things I'd love to chat about if no one.
Please.
And apologies for the no camera. We have kids out of school, so it's a little chaotic here, and I'm saving you all from. A little bit more about the question about unlabeled training data, because maybe that's not instruction fine-tuning, but my understanding is you wouldn't have to go back and start training again, right? That we could, because we did this once before with a project where you could take a model, and maybe it's a different kind of fine tuning, but there's a way in which we could do it to represent language in particular ways, if you know where I'm getting at.
So the difference there is that what Iman was talking about was parameter efficient fine tuning. And so with that, in that particular, that was LoRa. And what LoRa does is it adds additional parameters to the model. So it does a matrix multiply often around the weights of the attention mechanism only. And then for learning, all you're doing is you're modifying those weights. So it's sort of, it's giving you a way to modify how the attention is working without having to retrain everything, right?
So it's really only modifying the attention with additional parameters. It's not actually going back and doing any updates to the weights of the originals.
That's right. It can, but or it doesn't do. That's right. So the weights. So with LoRa, for example, you can pull those out and you can have like different versions, and you just sort of plug them in, right? And so
it's on top. Okay.
And sometimes with LoRa, there are versions of it that will also do that with the feed forward network. So there are going to be some approaches where you could do causal modeling, which is that doing the training of the model again, but more likely you would do actual full training of all the parameters, right? Because you can always do that. Now the question is, can you do that with a later model? And you could do additional causal language modeling, so training it on concepts, even after you do instruction fine-tuning, but that will be disturbed, right? So it's kind of like, but it's an open question, how disturbed will it be? Does instruction fine-tuning still work as well after you do additional causal modeling? But what we do know is that, man, reinforcement learning from human feedback, that DPO and the PPO, because those are like external functions that you're trying to maximize, that really messes with all the weights. And so trying to go back from there is hard, so that's why you find people will do instruction fine-tuning even, when it might be more efficient to try to do it using PPO or DPO. They may just use instruction fine-tuning, trying to get it to act a certain way, because at least with that, you can do additional training on it. Once you do DPO and PPO, it's kind of, I don't know, maybe some people do it, but boy, it's not, because you've disturbed a whole bunch of things when you've done that. Sharo, do you agree? Have you seen any examples of like doing additional training once you've done that DPO or PPO? Yeah. So it's a matter of compute, how much hardware you have to actually do the training. Can you do causal modeling in a parameter efficient fine-tuning way? Possibly. I'd have to look more at whether people have done LoRa and then done more. You almost certainly haven't done QLoRa, which is the quantized version, because once you go quantized, it's like you've lost a lot of that subtlety, and you're really counting on that for it to be able to learn new concepts.
Okay, so we just go back earlier in the chamber.
Yeah, go back earlier. Exactly, that's right. And maybe worst case, you have to go all the way back to the training, right? So, and the way that I think about it is, if the component parts are there, you might be able to do a parameter efficient fine-tuning, but it's more like reshaping what's there rather than creating wholesale new knowledge.
Yeah, I need to think more about the conceptualization, because it's not about adding new knowledge. It's about reweighting. Because I mean, if you think about human language, right, when you're talking about predicting the next word, in fact, the next word for Jesse, Umang, Abby, me, right, would actually be different. And we were thinking about ways to try to bring in some of that subtlety. So it's, how do I explain? It's less about overall knowledge base and more about, this is making sense.
No, this is. No, and I think
but not at the level of a human. We're not looking to do it for an individual human. We're looking to represent perspectives.
Yeah, that might be approachable using, the parameter efficient methods. But again, if that is your direct research interest, doing that with parameter efficient models, great. But if not, train the whole model.
So my question when you said the train the whole model, and maybe I'm extrapolating poorly, but back when we did a whole bunch of word embedding models, right? We would start off with the big old word TVEC and then bring in our data, right? We weren't training it from scratch. That's what I'd sort of imagined. So retraining, but training using some, starting with the base model, and right, is that what we're talking about? Not training, because we don't have enough data to train.
Yeah, not from scratch, right? But if you are, so really it's supervised fine tuning. It's just another kind of supervised fine tuning. It's where this task is where you're having it produce the next word. So you're continuing, what you're doing is you're continuing the training that originally trained the model.
Well, that's what I was wondering, because it looked like when you had those supervised training sets that Among was showing, in fact, when you put it in, it's actually collapsing them all together, right? It's got the instruction, the input, and the output as a single text block. So in fact, we could just take text blocks that are other text blocks and perhaps try them there.
Yeah, you could. I mean, it's because we call it instruction fine tuning, which is a special type of supervised fine tuning, but really it's all about given this input, produce this output, right? So if you can make it work in that framework, terrific. That's great. If it doesn't work in that framework, then you can do, more explicit causal language model training. Yeah.
Okay.
And the big difference is you're going to have to get a lot more hardware behind if you're doing like supervised fine tuning without the parameter efficient, right? If you're like, if all weights are game, then you're going to be training, even like the 7 billion parameter, you're probably going to be doing that training on one of the DGXs. If you want to do the larger ones, like the 70 billion parameter one, that'll just squeak in on one DGX. Probably would have it on 2 or all 4 of our DGXs to do that training, but it's possible.
Great. Thanks.
Absolutely. Other questions?
There was a news article that came out yesterday reporting on that the Agency for Healthcare Research and Quality and National Institute of Health on Minority Health and Health Disparities had created a framework to address algorithmic bias in healthcare AI needs.
Really?
Yes, it was just released. I'm working on 2 different machines, but I can try to it's on healthitanalytics.com, and I can try to transition it to the machine that the Zoom is on. But it seemed to me, based on reading the article this morning and then listening today, I'm curious as to the intersection. I wish I knew enough to be able to ask a better question, but my curiosity is sparked. Like, could we use what we learned today to train an algorithm in healthcare IT?
Oh, what I see. So they identified key principles of, So it's kind of like setting the framework for, so, okay. So one way that people have tried to address bias in the models is to do reinforcement learning from human feedback, right? But that is almost like a Band-Aid. It'll address specific types of queries and will sort of correct for specific types of queries or kinds of responses, but those representations are largely unchanged underneath, because the model has been trained on what it's been trained on. So, I mean, like think of, I don't know if you remember from a few years ago, but the liver enzyme tests that had different values for different cutoffs for different racial groups, right? That was in the test, right? That was like the design of the test did that. And that the model's been trained on that, reinforcement learning from human feedback is not taking that out because that's in the model. And now it's been changed because they realized, wow, it's really racist, because the whole thing behind it.
Yeah.
You remember that? Yeah, exactly. Which was just insane. But that's, so if it's inherent in the data that you're training in, then it's a real question of, well, like, what does it mean to try to get it out of the model? you know. So I'm going to take a look and see, but so the tools that we talked about here can ameliorate, RLHF, that could ameliorate at least the immediate responses, especially when it's a chatbot kind of environment. But if what you're doing is you're doing embeddings and you're making predictions, you might be doing an analysis of each and every solution that you come up with for its downstream effects to see if it has differential effects, for example. And it looks like that's some of the things that they're talking about there. But can you make a clean model?
Yeah, that's a great question. So in trying to think, well, I'll just pause in case someone else has something to jump in. I know most of the team on here is, but if Him has something, I don't know if Him is on your team or not.
No, Him's not on our team, but Hem, did you have a question?
I have a little bit of a kind of philosophical or conceptual question going on here in my head. Even with all these supervised fine tuning and the kind of outputs that we are getting is very good for subjective outputs which we want, right? So summarization, creative, writing, etc., etc. However, if one were to do, let's say, more deterministic output, which is what most of the time we are used to software doing things for us. I think that's where, the outputs are getting to like 60, 70, 80% is what, at least what I'm reading. And that with lots of, experimentation have to be done. So philosophically, I think so should we think about this as two very distinct types of software applications, and this is the one which will help us with the creative and the pure white collared world, and then we should leave it the traditional software the way traditional software is? Or is this the whole class replacing, or in time can replace some of the traditional software? So it's a little bit, as I said, conceptual, but if you could entertain a little bit, 5-10 minutes, a few points, I would love to hear the feedback.
Sharo, did you have some thoughts? I saw you thinking.
I'm on the fence right now. I'm on the fence of that. Yeah, I think before I really had a true comment on that, I would need to see some of the more advanced models. But in the current moment, I just what kind of software are you thinking about?
No, I'm just thinking, let's say your traditional ERP systems and CRM systems and, very, very traditional stuff that we are used to seeing, and software applications the very hyperbole of all these things where, we are seeing the extreme version is look at OpenAI's valuation and where it is like it can disrupt, Oracle and, 65 others, Oracle, SAP, and, take along half the industry with it. And, that's where, they have been put on a pedestal, that's where they would be, right? On the other side, the reality is that, yes, I think this is all still getting 65, 70% kind of accuracy, and that, GPU hungry, expensive to run. Yes, I think experimentation, phenomenal tools, phenomenal democratization, people like me can, now have access to things which otherwise required PhDs to do things. So yes, I think there is a little bit over there, but I think where I'm trying to get to is where is a little bit of the reality, or again, where do you see this, going a little bit, in time? That's what I said. A little bit, not exactly tight, but at the same time, just a little bit connected to how we invest our time and focus on these things.
So one thing that I'd mention there is that so think about tasks for, you mentioned CRM, customer research management, relationship management, pardon.
Yeah, sure, all good.
So because these tools, these models can be tool users. So one way is you might have a new kind of front end, right? Find me all the customers that are like this customer. Okay, right. Then what the model will do is generate, code that would call the CRM solution that you have with, with particular parameters, right? So it's not replacing everything, but it may be the new interface, where it's a tool user and it calls, or even so that the most disruptive, where you see the sort of this the tool being used for the human interaction and the interpretation, and then but existing tools being used otherwise. Think about dashboards. So dashboards, you build a dashboard and yeah, sure knows where I'm going on with this. So you build a dashboard in the hopes that you can create a representation that will answer the question of all the different users that will use your dashboard. So you might have different pages and pages, you might have drill downs, you might, you can do that, or you can have an LLM that has information about, just like documents detailing what information you have, and also knows the table information. And so you say, hey, I want to know, I want to know all the students that were in these kinds of classes. And, and I want to have, sort of a breakdown of who they were and what their majors were. Great. What it does in the background is it generates SQL code. Right? And then it answers your question and can even generate code to generate visualizations.
Yeah.
So,
I can see that. No, I can see that. Maybe definitely it's that mystique, unknown that we are kind of going into. But I think, yes, it could lead into, and yeah, I think, now that I think about it, I think it was exactly, like the 2008 iPhone moment, where I think people, could see a completely new way. And then everybody, from academia to industry to line leader thought, hey, what if my salesperson could have this? Or what if my clinician had access to the tablet? And that's what we are living now, 12, 15 years out. But yeah, thank you. Really appreciate you guys entertaining that. Sharo, any thoughts?
I think my thoughts mostly revolve around, I don't know how to explain it, but essentially my thoughts revolve around the proprietary nature of some data that only some companies have, and some of what we would want, like for us as general people to use, is really very much owned by those companies. And so sometimes I do wonder about the extent to which the common man will be able to actually benefit from certain things, because so much of the data that you might want to build an LLM with is just held by a company. So for example, I have an interesting time making diagrams, and I have asked Dolly like a lot to try to help me make diagrams, but Dolly cannot make a diagram, like it cannot. And so who has all of the data about generating diagrams? It's not me, it's not you, it's whoever makes diagrams. It's PowerPoint, it's who those people. And so it's just the thought of that, like sometimes, like I'm not sure how we as people might be able to, like in an open source way, like really benefit from some of these models, because we don't have the data to be able to actually like create the things in an open source way. So I don't know. I don't think that was actually asking your question, but it has just been something that I've been thinking about a lot, especially because I've been making diagrams lately. And then I think the second thing is sometimes with software, I don't know, I will be interested to see how the LLMs for code evolve. I have used GitHub Copilot like a lot, like so much. And sometimes it just does these odd things that I truly would not expect from any software, anything that was not like the beginnerest of beginners. And so I don't know, it's just interesting to see how sometimes that they can do things that are very advanced, but then at other times they will fail on like the simplest things. And so it's very much to your point of how we see that thing, like those things going along in industry. If you need something that's more deterministic, it can't be like, writing a for loop and then like it's in Python and has like a semicolon in a weird space. Like it's, yeah. So I don't know. It's interesting. It's something to ponder for sure.
Yeah, no, thank you so much for entertaining that. Thank you, everyone. Have a wonderful rest of the day.
Bye.
Welcome, Bill. And Bill's gone. All right. So other questions, Michael or Daniel?
I don't have any questions right now. I think I'm going to think about this a little bit and look forward to the time tomorrow, and then bring some more questions a week from tomorrow. Once I have some more time to think about it. Dan, do you have anything?
No, I'm kind of in the same boat. I'm just kind of crashing the party to learn. There's so much to this world and to the language. I'm just trying to absorb. It's just interesting hearing the stories and your all's insights on your own experiences. So yeah, but I hope to continue the journey with Michael. He and I are working together, so you probably see more of us.
Fantastic. And and I'll mention, of course, the my semester-long class, and also we'll have our AI summer as well, where things will change immensely again before we have that, and there'll be more time to sort of dive into those as well.
Great, thank
Oh,
you.
yeah.
That's great.
Oh man, you actually got on to Zoom though from Linux. That's impressive. Bill, did you have a question? You can just type in the chat if you'd like.
I'm gonna go. Thank you, guys.
All right, bye, Michael. So yes, so we do have well, we have our on-prem ChatGPT-4. It is still in beta, but Jules White has been working on this, and he does have. So we've been working on that. We've been trying to strike a couple of different deals. I'm unsure where we are right now, but he says we have level 2 security, which means that we can get sensitive data in there now. So I myself am going to be using that early on in the semester for some work with the Faculty Senate. And we're going to be talking a little bit about that tomorrow. And for the folks here, I was not able to get Jules yet, so I don't think that he's quite back yet. So we may just have to do a later workshop for that. Other questions, Phil? Okay, yeah. Do you have other questions? I think you could use it. And I'd be, if you want to send me an email, or you can just write Jules White directly, describe what you would like to do and say, I'm interested in being a pilot user and giving you feedback. It's jules.white at Andy. Excellent. All right, folks, then I think we'll finish up a little bit early. Great presentations today. So thank you all very much. This was a lot of material. I loved seeing the examples. Charo, I love your slides. Did you do all those from scratch? Did you start with anything, or because I love those?
I started with the AI summer from last year, and then I started using IndyDev, and it makes great slides.
Ooh, oh, that's fantastic.
On Jupyter Notebook, lots of slides.
Fantastic. Oh, that's great. Well, I'd love to either and I think some of this would be and slides. Yeah, Charo is gonna figure out how to get those out to folks.
The last mile, how to get it on GitHub.
Would love to use that in the undergraduate class. Would love to use them in the transformer class as well to get some more material there. And then I think that we could also use it for oh, those are the only 2 classes. Yeah. All right, I'm going to close it up then. See you all. Take care. Bye. Bye.